Good afternoon, everyone. Thank you for tuning in. This is Team Mars Train, and we're going to just jump right into it. So here's our team photo. This is all the members of our team who contributed on our project. So the baseline for our mission is that you cannot land in the same spacecraft that you will use to leave because in situ resource utilization is not at an advanced enough level in order to refuel a spacecraft in a 30-day period with the amount needed. Additionally, planetary landing is an unpredictable process, and this is because various environmental factors such as atmospheric conditions, parachute physics, and this results in a landing ellipse, which is a region of uncertainty where there's a possibility, a high probability that you will land within this certain area on the planet. And so when you're landing multiple assets, you can't have those ellipses overlap, otherwise they could collide assets or land on top of each other. So this necessitates traveling from the vehicle that you land in to the vehicle that you leave in. And so our team decided to make that the fundamental means of exploration for our mission, is that movement from point A to point B for this mission. And so our Mars train design provides the surface crew with two options in order to get them to the ascent vehicle in that 30-day period. So broadly, the mission scope, the reason that this theme even exists in the first place is to expand the limits and knowledge of human interplanetary travel. And so our team identified 4 goals that we want to achieve with this mission. That's to achieve the first landing of humans on another planet, to retrieve surface and subsurface samples for further study, to understand the effects of interplanetary travel on the human body, and to search for signs of extraterrestrial life. So this image is taken directly from the RASC-AL website. So this is, to break it down, what this means bottom line is that there's a crew of 4 going to Mars. 2 are going to go to the surface, 2 stay in orbit. It's a 30-day mission on the surface. They'll have access to a pressurized rover that will be able to drill core samples. They must leave before the end of the year in 2035. They have 3 landers to use to deliver 22 metric tons each to the surface. And we have to follow NASA technical standards 3000, 3001, and NASA's Human Integration Design Handbook. But broadly, the overall mission timeline looks like this. The assets will be pre-positioned in late 2030 and arrive in 2031. And then once we reach the next phase where Earth and Mars are lined up more closely, the crew will launch in 2033 and they will return home by 2034. So for a day in the life, this is a short little breakdown of what their lives will look like while they're on the Martian surface. So it's important to note there's an extra 40 minutes in a Mars day compared to an Earth day, and that's accounted for in their sleep schedule. So the astronauts, this is another important thing that we want to mention, is that the astronauts will conduct EVAs for no longer than 5 hours, which is shorter than the longest recorded EVAs from the Apollo missions. So you can see that diagram on the right. And now I'm going to pass it off to Will to go through some more information on the day-to-day activities of the crew.
Thanks, Siler. 2 astronauts will land with the buggy in the Mars Crew Lander, the MCL for short. The buggy will exit the MCL and await the astronauts, where it will be driven to the Oddity rover, which arrived on Mars in its own lander 2 years prior to the MCL. Once Oddity is found, the buggy will be attached to Form Train, the Transit, Reconnaissance, and Investigation Navigator, where they will enter Oddity through the suit ports, leaving the extravehicular mobility units, the EMUs, attached to the back. Every morning, Train will be driven to the next waypoint en route to the Mars Ascent Vehicle, the MAV. During the mission, communications are made with MAGIC, the Mars Acquisition Guidance and Information Communicator, as well as the Mars Command Module, the MCM. Once Train has reached the waypoint, the astronauts exit through the suit ports and place down solar panels so that Oddity can charge during the day mission on the rover. During the day mission, 1 meter cores and surface samples will be collected. They return back to Oddity to rest and repeat for the rest of the mission. At the end of the mission, they find the MAV, which will take them from Mars back to the MCM, ready to go home to Earth. Now I'm going to hand it off to Tyler, who will talk about ConOps.
So here's a full ConOps diagram of the entire mission. Mission will start with 2 launches from SLS Block 1B cargo. First would carry the communication satellites and the ascent vehicle. Second would carry the rover and the crew lander. And the third would be the SLS Block 1B crew and would house the command module for the return journey, the astronauts, and some supplies for the mission. After they rendezvous with the lander in orbit, 2 crew members will go down, they'll do the mission, and they'll return the MAV in orbit and then head home. So here is an ops diagram of the Mars portion of the mission. The two crew members will land near where the rover is in the buggy, and they'll drive to it and hook up. They would then travel across the Martian surface to where the MAV landed, collecting rocks and regular samples along the way. This would take approximately 30 days, and then once they load up the samples in the MAV, they'll leave the buggy and rover behind and head back into orbit and then home. A key objective in this mission is searching for signs of life, and where there's water, there's life. Exploration areas to consider are those with ice or where water once might have existed, like in subterranean water deposits or beneath hydrothermal pools. Another thing to consider is signs of carbon, as carbon is a building block of life. We will also be collecting rock samples, as our composition will help understand how the Martian surface has changed over time. Rocks below the surface will have a different composition than ones above surface, which would help understand what Mars would have looked like millions of years ago. Different areas could also have different compositions, which would lead to the theory that there would be climates on Mars. We hope to collect the same amount of samples as above the surface and below the surface, roughly, in the range from 0.6 to 1.3 meters below the surface. The space environment will also affect the astronauts during this long mission, as prolonged exposure will weaken bones and muscles. We hope to use this mission to plan for future missions as well. The crew that lands on the surface could have a lessened effect from this because they will be experiencing gravity during the 30 days, but the long trip back might debunk this theory. We will also be monitoring the radiation levels that the crew experiences on the journey back.
So Tyler just finished talking about the science objectives. I'm going to go a little bit in depth about the landing site. We chose Northeast Sirius as our landing site, this being that the major focuses of our mission are to discover life and decipher the nature of the changing environmental conditions on Mars. The Nochian surface has records of polyhydrosulfates. This suggests that there were surface bodies of water and active groundwater during the Nochian-Hespian transition. This next slide shows the path that the two astronauts on the ground plan to take. The image on the right shows you the path through geological areas of interest, and the image on the left shows you 3 ellipses showing you where the MCL, Oddity, and MAV plan to land, as well as a yellow box showing you the range of where the buggy can travel away from the rover. Now I will begin to talk about Mars Train. The concept is a mobile base which allows for a mobile form of exploration, also allowing for astronauts to cover more ground on the surface. There are going to be 2 main bodies, Oddity and the buggy, which will be connected in a train-like fashion as shown. Both will be powered by solar panels that are stored on the outside of Oddity and deployed during the day. The buggy will charge overnight while hooked onto Oddity and used for exploration on the surface during the day. Both will have compatible wheels in case of a wheel failure or breakage, as well as autonomous navigation capabilities. Here we have 2 images of Oddity. We decided to model Oddity after Space Exploration Vehicle, also known as SEV. Oddity will contain 2 major parts. It'll have the front cockpit area, which can be used for exploration in case of a buggy failure. This is very important. If the buggy fails, we would like to continue our science objectives and mission as a whole. The front cockpit area will have the ability to kneel, dig, and a wide range of view. The second area is the living quarters and storage area, which will be used for sleeping, hygiene, personal time, and exercise. It will contain sanitary facilities, including a privacy curtain and misting shower head for sponge baths. The dimensions and mass and color for Oddity are below. Oddity will be powered by an area of 13.5 meters squared of solar panels. This will be broken up into 4 solar panels attached on the side, each with a mass of about 20.25 kilograms. This will weigh approximately 75 newtons on Mars, which is within reasonable range for the 2 astronauts to take off and deploy during the day. As far as wheels and movement, Oddity will contain pivoting wheels that enable crab-style movement, which is excellent for the rough and rocky terrain on Mars. There will be 12 wheels designed with open structures rather than air-filled tires. Oddity will be able to drive 10 kilometers an hour in any direction and climb up to 40-degree slopes. As far as docking, there will be suit ports located on the back to allow for rapid ingress and egress. This also allows for the crew to wear normal and comfortable clothes inside Oddity, as well as keep the inside free of outside debris and minimize air loss when depressurized. For communications, there will be a 1-meter diameter antenna, a 1-meter omnidirectional antenna, as well as a laser communication device for MAGIC. Samples will be stored in containers on the outside of the rover located on the back. As far as the buggy, it is going to be white. We went ahead and added a solar panel on the front face. That way it can charge while it is away from Oddity, but the main power will come from when it is charging overnight. The wheels will be compatible in case of a wheel failure as well. This slide explains the solar panel sizing and where we got the number 13.5 meters squared from. So we used the energy consumption requirements based on the NASA SEV, which is also similar to an electric car on Earth with about a 500-mile range. We decided to choose a Tesla Cybertruck since this is similar in weight and range. And we decided to double the baseline to account for buggy charging and any additional onboard powered systems. As far as battery requirements, NASA's energy requirement for the SEV is 200 watt-hours per kilogram. However, this was from 2012, and nowadays modern commercial batteries have already surpassed this number. So we went ahead and used this as a conservative estimate, which gave us an oddity battery no heavier than 50 kilograms. The buggy battery will be about half the size.
Now I'll talk about the wheel and suspension design. The wheels must maintain traction on the Mars surface and withstand rough terrain. They must maximize durability to weight ratio. They should be robust to potential failures. This rules out inflated tires, as a puncture could end the mission. They should be easily replaceable and repairable by crew in the event of failure. The Oddity and the buggy will also use the same wheels so that they can be interchangeable. The suspension must have the ability to handle rough terrain and overcome large rocks. They must withstand the forces applied to them from all directions due to uneven terrain and speeds higher relative to previous Mars-based rover missions. They must spread weight evenly across wheels to improve traction. Keep the rover level, climbing rocks and inclined surfaces. On the left is the open wheel design, like used with Curiosity and previous rovers. This specific design is based off the Mars Concept rover, will be made largely from titanium and carbon fiber. Also made from titanium is a double wishbone suspension design based off NASA's Space Exploration Vehicle suspension. Active suspension will be used to keep Oddity level and improve traction, and will give Oddity a wider wheelbase. Now I'm going to hand off to Sila, who will talk about trajectory.
Thank you, Will. So now I'm going to go into the mass and trajectory analysis. So this mission is going to be able to be accomplished in 3 SLS launches. We're assuming the use of the SLS Block 1B variant with a C3 of approximately 12 kilometers squared per second squared. And we have some more information on how we got to these numbers in the backup slide. So that means that the total payload delivered to Mars orbit is 33 metric tons. And by looking at previous heritage designs, we've found that approximately 1/3 of the mass that is landed is comprised of using EDL systems. So that's how we believe we arrived at the 22 metric ton limit to get stuff to the surface of Mars. So the first 2 launches are going to pre-position all the non-crew assets. So that's the Mars Ascent Vehicle, the Mars Crew Lander, the Magic Constellation, Oddity, and Buggy. So the 3rd launch will send the crew to Mars, and the trajectories and mass breakdowns are coming up. So for the first launch, all these calculations were formed assuming that the MAV needs to supply 5.3 kilometers per second to rendezvous with the Mars Command Module. So as you can see in this mass breakdown on the right, the total mass of this entire MAV with its EDL system is around 23.5 metric tons. So that leaves a little bit of extra room in that 33-ton limit. But we wanted to include something that will last beyond our mission. So these 3 satellites from the Magic Constellation, or that form the Magic Constellation, they're around 1.5 metric tons each. So, and they don't need EDL because they'll be in orbit of Mars. So this brings the total mass of that payload of the first launch to around 28 metric tons. The second launch will consist of Oddity and the MCL and Buggy. The total mass of Oddity is around 4 tons, so around 6 tons with its EDL systems. And so the total mass of everything together in this one payload is going to be 27.9 tons. And the MCL itself will contain the ground supplies for the crew and all the supplies needed for them to return home. The final launch will consist of the Orion capsule and the crew's living quarters, as well as their supplies to get them there to Mars. And so we found that there's an additional around 11 tons of unused mass on the first 2 launches, which will likely be used for additional propulsion systems or fuel to return the crew to Earth. So now for the trajectory design. So these were created by the students. The trajectory on the left is to pre-position all the assets, and the trajectory on the right is the crewed portion. So to break down what you saw on the previous slide, the asset pre-positioning trajectory is around 4.8 kilometers per second for a total delta V. They launch in December of 2030, arrive in January of 2031. The second launch is in January 2031, and they'll arrive in October of 2031 after around 300 days. And the crew portion requires a bit more delta V, but that's why we're going to send ahead some fuel and some propulsion systems. And it'll launch in April 2033, arrive in October of 2033, and then they'll get back to Earth in July of 2034, with the lowest solar range being 0.6 AU, and we'll discuss how we're going to tackle that issue. So an important thing to take into consideration is that Mars has a larger J2 and J3 than Earth, and Jupiter will be in conjunction with Mars during the period that the crew will be at Earth. So the MCM, we've found that it precesses a very large amount over the 30 days by around 300 degrees, whereas the inclination doesn't change by a lot. So as you can see in this figure to the right, this is just another visualization of that. This is propagated only over 2 days. And so this propagator included accelerations from J2, J3, the Sun, Jupiter, as well as solar radiation, pressure, and drag. And so it's going to be important to make sure that the initial orbit is determined such that it will pass directly over the MAV on their final day. Another important thing to talk about is in-transit aborts. What happens if something goes wrong while they're on their way to Mars? So there's two options. Either they're close enough to Earth that they can perform a deep space maneuver, either return quickly back to Earth or come back around like you see on the figure on the left. Or if they're closer to Mars, do a powered flyby that is either just a powered flyby around Mars or also get a Venus gravity assist as well. So now I'm going to hand it off to Alex.
Thank you, Siler. We're now going to focus on the mission cost estimate. We've estimated the budget 2 ways, one from similar past missions and the other using the advanced missions cost model. Using the past missions, we estimated the Mars train mission to be about $45 to $55 billion. And using the advanced missions cost model, we estimated to be around $44 billion. We're adding a 35% margin for other parts of the mission, so the new total just comes below $60 billion. This will be roughly 12 to 15% of NASA's budget from now until the initial launch date. Focusing on the landers, the RASC-AL mission will use 3 22-ton payload capability landers. We are using the SLS Block 1 cargo for the size and weight limit. Each one must have a capable EDL system for Mars entry, and we are focusing on a one-way lander design. 2 of the 3 landers will prioritize cargo, and the other lander must be capable of supporting life, and this one will be the crewed lander. We are going to be using the Apollo missions for architecture for the crewed lander. It's outdated but highly successful. Out of the manned Apollo missions, only Apollo 13 was the one that did not make it to the moon, to the surface of the moon. Using modern technology with the general architecture, it will most likely yield a reliable first design. We also have recent Mars missions like Insight and Opportunity for unmanned cargo landers, so there is vast heritage there that can be used for further iterations. The propulsion system must be capable of landing 22 tons of cargo safely onto the Martian surface. The EDL system must have a heat shield, retro thrusters, and supersonic parachutes. So the design is a bottom-up design of a blunt entry vehicle for the initial model. Thrusters, spare thrusters are also included. A supersonic parachute will be inserted at the top of the design, and a heat shield will be required to cover the entire bottom section of the lander. So now I'm going to pass it off to Sebastian.
To implement these instruments into our mission, we would have to look into the 3 different vehicles that will land on the Martian surface, which are the Mars Ascent Vehicle, the Odyssey rover, and the Mars Crewed Lander, and look into their different landing requirements and ways of applying these instruments into these specific landing vehicles. So looking into these vehicles, first of all, the Mars Ascent Vehicle would use an EDO system that would involve a heat shield, of course, a supersonic parachute, some retro rockets, that will allow it to safely arrive to the Martian surface, which is similar instruments to the ones used by the InSight lander. The Mars Crewed Lander, which would use a similar system, but of course it would include the crew and the buggy, and it is pictured in this rendering right here. Finally, the Odyssey rover would use an EDL system that completely encloses the rover into a way that it's safely packed. And so once it arrives to the Martian surface, it can simply open up and allow the Odyssey rover to drive off and just wait for the crew's arrival. And so now we will talk about communications.
The communications network has been developed to ensure maximum safety of the crew. We wanted to put a real focus on constant communication, and so we decided to create a constellation of relay satellites around Mars that will be 120 degrees apart. This will guarantee that the astronauts on the ground will be able to speak to either the astronauts in the orbiter or to Earth at any time. These satellites will be in aerostationary equatorial orbit of 17,000 kilometers, and the orbiter will be at 400 kilometer altitude, and these will be able to speak to each other. With a round-trip Earth transmission time of 44 minutes, this network allows the orbiter team to work instantaneously with the ground team, giving them the quick support if they need it. On the right, you can see our interplanetary connection, and these show the uplink and downlink data rates. These are the minimum requirements we need to produce HD live stream video straight from the camera of the astronaut on Mars. How do we do this? We use the MAGIC satellites. The MAGIC satellite stands for Mars Acquisition, Guidance, and Information Communicator. And each satellite will be known as MAGIC 1, MAGIC 2, and MAGIC 3. The satellites will have a main bus of 2 meters by 1.5 meters by 1.5 meters. And these will mostly include the hydrazine and xenon fuel tanks. The satellites will also have 2 solar panel arrays on each side, giving an area of 24 meters squared. The satellites will also have 3 laser communications packages that will allow for large data transfer, up to 150 megabits per second per transmitter at just 76 watts. The reason for having 3 is this improves efficiency, as the whole satellite may not need to orientate itself, but it also allows for multiple transfers at the same time. This means that if a transmission comes from Mars, the satellite can relay it to Earth straight away. What's unique about these satellites is that they are hybrid. This means that they are capable of both RF and laser communications. And they do this to combat all atmospheric attenuation like Martian dust storms. They do this by employing a 1.5 meter diameter antenna. For propulsion, the satellites will have an ion thruster for orbit entry and large maneuvers, but will mostly be using the hydrazine thrusters and reaction wheels for attitude control. The problem with the ion thrusters is that they can take a very long time to accelerate. The team has accounted for this by ensuring that these satellites will be placed in the first SLS launch so that they can target their orbit early and be in place well before the humans arrive. When the mission ends, these satellites will stay in Mars orbit and can be used for future Mars missions. As well as in the air, the communications on the ground is just as important. The Mars rover will have a laser communications package that will involve 4 uplink transmitters and 4 downlink receivers. The system is capable of high data transfer, and it can be used so that the orbiter team can remotely drive the rover. The system is also capable of a Martian to Earth transmission, but power is limited and there can be difficult pointing capabilities to overcome, going through both Martian and Earth atmospheres. Ideally, the strategy would be to send information via the relay satellites, so they take most of the data transfer workload to conserve energy on the ground. The rover will also have a backup 1 meter high gain antenna and an omnidirectional antenna for emergencies.
Spacecraft power budget. We know that our power subsystem must produce a continuous output of electrical power for the entire duration of the mission. Orion's current configuration, equipped with 4 solar wings, each with 3 solar panels and 15,000 solar cells combined, can supply 11.2 kilowatts of power to the spacecraft. The power budget constructed used percentages based on historical calculation for unmanned spacecraft. It was assumed that on the onboard ECLS would require 20% of the power output, so we adjusted those percentages as seen in the table. Radiation protection, GCR shielding. Radiation protection shielding is necessary for both the safety of the crew and the reliability of the electronic instruments used during the mission. In order to protect from galactic cosmic rays and solar energetic particles, a standoff shield, as shown in the image,
will be used to protect the crew and spacecraft during flight. A material that is currently being tested is hydrogenated boron nitride nanotubes, which has the potential to work as both a shielding and structural material. While still in the research phase of implementation, it has great potential in its high heat threshold for stability and its ability to absorb harmful radiation.
According to NASA, one astronaut requires 0.84 kilograms of oxygen per day, putting the total for a crew of 4 at 3.36 kilograms every single day. Using electrolysis to separate hydrogen and oxygen molecules in water, the oxygen generation system can produce between 2.3 and 9.2 kilograms per day, whatever you decide to set it at. The system itself has almost a 22,000 hour lifetime, and our mission is only about 11,000 hours, which puts it well within the lifetime of the system. The oxygen generated from it will be mixed with nitrogen that's stored on board, and it'll create an Earth-like breathing atmosphere. Trace contaminant and particulate control is needed to keep the chemical and particulate concentration to allowable levels in the water and air. In particular, keeping the Martian regolith particles out of the rover is really important because they have average diameters of 3 micrometers. Allowing these particles in could harm the astronauts if they breathe them in or harm equipment by clogging it. In order to keep these particulates at a minimum, both passive filters and active scrubbers are necessary. Activated charcoal scrubbers actively pull contaminants from the air, and high efficiency particulate air filters catch the contaminants that make it past the scrubbers. A water recycling system will be used that should reach a 98% recovery rate in order to maintain a water supply on the mission. Wastewater, including moisture in the cabin and water extracted from the crew member's urine, will be collected to reach the desired high recovery rate. It is disinfected using both filtration and oxidation, as well as silver biocide to keep microbes from growing during storage. Because of the distance from Earth, the water quality will need to be monitored on board because we can't wait for that delay from Earth. The crew's environment needs to be monitored closely to ensure a safe living environment. A gas monitor will be used to monitor the cabin's atmosphere and ensure safe air quality. Microbial monitoring will identify and characterize microorganisms using molecular-based methods. And onboard analysis of cabin air and measurement of particulates will make sure that the air does not have any dangerous particulates in it. The lack of gravity experienced in space and on Mars can cause issues with spatial orientation, coordination, vision, and muscle loss. Without Earth's gravity, the fluid in the body tends to float upwards, which can create fluid buildup behind the optical nerve, causing vision problems and hinder the crew member's ability to execute tasks. Compression cuffs located on the thigh can help keep fluid evenly distributed throughout the body. For coordination and spatial orientation, self-administered tests will be used to monitor the crew's balance, fine motor skills, and fitness during the mission. In order to maintain muscle mass, regular exercise will be required using things like resistance bands to combat the lack of gravity. Along with this lack of gravity, living in a closed environment can affect the crew member's health as well. Stress hormones are often elevated when people are kept in small quarters for long periods of time. LED technology can be used to change the color of the cabin's lights to enforce healthy sleeping schedules. The immune system and the microbe characteristics can change while traveling in space, which puts the crew member's health at risk. In order to ensure that the crew stays healthy, frequent blood and urine samples will be analyzed to monitor their immune system.